Welcome to the BLM Mountain Fire Aviation Training. I'm Meteorologist Steve Hunt with the National Weather Service, and I'll be presenting this briefing. Here is a little about us. We are the National Weather Service Weather Forecast Office in Elko, Nevada. We provide the weather forecast to KBAM in the form of a TAF and forecast discussion. We also issue all advisories and warnings that will impact the area. The CWS2 in Salt Lake City also provides additional forecasts and briefs for aviation in the area. Jumping into Battle Mountain, the airport was built in 1942 to serve as an auxiliary field for the U.S. Army. Both of the runways are 7,300 feet by 150 feet, maintained asphalt in generally good condition, and are at 4,530 feet MSL in elevation. The runways are orientated to be in line with the valleys, with R3/21 orientated northeast to southwest and R12/30 orientated northwest to southeast. The main operators out of the airport are general aviation and fire aviation teams. The airport is surrounded roughly at each cardinal direction by mountains. Battle Mountain is to the north, North Peak is to the west, Mount Lewis is to the south, and the Argenta is to the east. Two major valleys intersect at KBAM, the Humboldt River Valley, which is roughly east to northwest, and the Reese River Valley from the southwest. This local topography plays an important role in the summer wind fills for KBAM. The wind flows predominantly from one of the western valleys over the airport during the summer. Reese River Valley funnels winds across the airport from the southwest direction, which is most notable during the afternoon hours. The Humboldt River Valley's northwest branch funnels winds from the northwest to northerly directions. Other wind directions are relatively blocked by the mountain ranges, besides weak nocturnal drainage winds. Looking further around, northern Nevada terrain is composed of many north to south orientated mountain ranges. These ranges are separated by broad desert valleys. Nevada itself means snow-capped, which is in reference to the numerous mountain ranges that are located within the state. These ranges rise from a couple thousand feet to nearly 10,000 feet above the valley floors. Most of the ranges are composed of fairly rugged terrain with little access via roads. The valleys generally have shrub to mixed shrub and grasslands. There are, however, salt flats that support little to no vegetation. The mountains have mixed grass and shrublands to full forest, pinyon, and juniper. In southern Idaho, the mountain terrain is split by the broad, gently sloping east-west plain of the Snake River Valley. This region supports farms, or else is covered with native grass and shrublands. Eastern Oregon is composed of a similar terrain to Idaho, but with mountains and canyons. Orographic impacts vary through this region, but the most prominent is caused by winds flowing over the mountains. The flow over a mountain range can create local updrafts and downdrafts based on wind direction. The flow can create many forms of turbulence, such as waves, rolls, and rotors. Orographically forced clouds are another prominent feature through the region that can be a tell for turbulence and obscuration for terrain. Orographically induced turbulence, when present, is a major hazard while flying in Nevada. With a lack of clouds, these turbulent eddies are essentially invisible. The most common forms of turbulence here are stable mountain waves and breaking waves. Stable mountain wave turbulence looks like waves that have crests that stand relatively in place. A rapidly shearing eddy can also form in the lower levels, known as a rotor, where the waves interact with the surface boundary layer. Breaking wave turbulence forms near the mountains and generally will have only a single crest. This turbulence is erratic in nature as the waves break and reform during the event. The strength of the turbulence can vary drastically based on local conditions and wind speeds. As an example, rotors and breaking waves can produce extreme turbulence within a localized area, while the rest of the region has far less turbulence. Rotors and breaking waves typically are close to the mountain ranges and can be present and enhance risks for fire aviators if they are present. The wind direction relative to the mountain is also critical in that the windward side of a mountain will generally have an updraft, while the leeward will generally have a downdraft. This can also occur in the small ridges and valleys on a mountain itself. A readily visible hazard is orographically generated clouds. These clouds can form in various regions depending on how blocked the wind flow is over the mountains. The more blocked the flow, the more upwind the clouds would form relative to the mountain ranges. Typically, during the summer months, the clouds will form on the peaks and downstreams of a mountain if it doesn't result in thunderstorms. A useful function for the clouds is that they can be a visual indicator that could reveal turbulence. A cap and lenticular cloud are good indicators for a stable mountain wave with turbulence. Smooth roll clouds can indicate that there is speed shear turbulence in the region. Cumulus clouds and thunderstorms indicate convective turbulence is present in the area. Rapidly undulating, fractured, and/or shearing clouds may be an indicator of a rotor or breaking wave, and extreme turbulence could be present. This picture here shows a lenticular cloud from a stable wave with a sheared rotor cloud below it. A constant threat with clouds is that they can obscure the mountain ranges, as seen here. The other prominent land feature in this area is the broad, relatively flat desert valleys. The valleys, like the mountains, are generally oriented north to south, the exception being the east-west path of the Humboldt River Valley. In some of the valleys, salt flats that support little to no vegetation can be found, such as the Carson and Humboldt sinks. The salt flats are prodigious producers of dust through the region. The Snake River Valley is a broad, gently sloping valley in southern Idaho. This valley acts as a funnel for moisture through the region, the main impact being intensification of thunderstorms that cross from Nevada into the valley. Here's another look at a broad desert valley. Note the copious amounts of dry vegetation, mainly grass and shrubs. During the summer months, the region is mainly under or on the western edges of a high pressure system. This will generally lead to hot, dry conditions across much of the region. This is periodically interrupted with moisture flows into the region through storms or monsoonal pushes. Since KBAM is located in a desert valley, it is very susceptible to high density altitudes during the summer. What this means is while the airport may sit at 45-30 feet in elevation MSL, the surrounding atmosphere may be less dense. This low density makes it harder for aircraft to generate lift, lowering the takeoff weight of a given airframe and decreasing ascension rates. Density altitude may become so high as to prevent an aircraft from taking off or gaining enough altitude to clear terrain. Density altitude does change based on the surface temperature, such that while fighting fires, that there can be a change in density altitude from a valley to a mountain, or even over a burn scar to unburned region. The summertime is monsoon season for the Desert West. This generally takes the form of a four-corner high setting up in the desert southwest with hot and marginally unstable conditions. Moisture intrusions are normally from moisture evacuation or storms called atmospheric rivers that can source moisture from the tropics. With hot, marginally unstable conditions, intruding moisture tends to result in daytime thunderstorms. Two types of thunderstorms normally form in the region during this time: dry and wet thunderstorms. The difference between the two is in the name. Dry thunderstorms generally produce less than 1/10 of an inch of precipitation, while wet thunderstorms produce more than 1/10 of an inch of precipitation. Dry thunderstorms normally are higher base storms with a deep, dry subcloud layer that evaporates the precipitation before it reaches the ground, as seen here. Wet thunderstorms form with a lower cloud base and a smaller dry layer below the cloud, allowing for precipitation to reach the ground, as seen here. Dry thunderstorms are very efficient at starting fires through lightning, as precipitation doesn't hinder the fire. Wet convection is less efficient at starting fires, as it can put out the fires through the rainfall or dampen the fuels. Dry thunderstorms are also very efficient at producing strong gusty outflows that can create haboobs and exaggerate fire behavior. Thunderstorms typically form along the mountain ranges earlier in the day before drifting into the valleys. Further convection driven from the outflows of older storms is typical later in the day. Another region that is favored for thunderstorm formation in Nevada is a dry line, which typically is found in proximity to KBAM during the summer. During the summer, KBAM is also susceptible to haboobs and dust storms. Haboobs produced from thunderstorms can suddenly occur with any convection so long as the winds are strong enough and they rapidly impact the area. Dust storms generally form with a strong southwest wind, and as a result, dust will be picked up from the Carson Sink and Humboldt Sink and dripped over the airport. Local sources of dust can also be picked up by strong winds and can lead to localized lowering of visibility. Both of these events can lead to drastically reduced visibility within a short period of time. Both haboobs and dust storms can reach hundreds, if not 1,000 or more feet into the air. Another prominent feature of summer at KBAM is dust devils, which can have extremely strong winds and be several thousand feet in height. These can also spread fires by moving it over fire breaks and lines. Fires in the region are usually fast burning as the fuel supply is mainly short-term fuels. The fuel type is predominantly 1-hour grass to 10-hour sagebrush. This can lead to fires consuming large swaths but burn only for a relatively short duration. Ignition sources for the fire are mainly from lighting and human activity. Fires may smolder locally for a few days after starting, but typically need stronger winds to rapidly spread. Once strong winds start, these holdover fires can rapidly spread and quickly consume thousands of acres. Longer-term fuels such as juniper and pinyon are usually located at higher elevation in rugged terrain in mountains. This means the fires in the mountains tend to burn longer, but are still capable of rapid expansion, making them harder to control. At the start of the season, the grasses are the first to cure and be combustible. The sagebrush cures later and will be available for combustion a little later in the season. Due to the fields curing at different rates, it is possible to have a mainly grass fire burn a region, only for a later fire to sweep through the same region and burn additional grass and sagebrush. The typical region for fires also shifts through the season from the south to the north, as the fields in central Nevada tend to cure before the fields in northern Nevada. Typically, higher elevation and longer term fields are the last to cure and burn late in the season. Fires that reach or originate from mountains typically burn the longest, as they have access to the largest amount of fuels and the longer duration fuels. These fires can also quickly grow as large fires, as strong winds are more readily available at higher elevation. This has been a brief overview and refresher of local weather and features around KBAM for fire aviation. Included are helpful links to access different weather products in the video description. Stay safe and stay aware of your surroundings while fighting fires. If you have any questions, please contact the National Weather Service in Elko at 775-778-6720.